All right, today we're jumping into some of the most powerful ideas in software development, functional programming abstractions in Scala. Now, I get it. You've probably heard words like monad, functor, or applicative, and they can sound, well, pretty academic and intimidating, right? But stick with me, because I promise you, by the end of this, you're going to see them for what they really are. Simple, powerful patterns that you're very likely already using every day. You just don't know it yet. So here's our game plan. We'll start with why you should even care about these patterns, then we'll build everything up step by step, starting with how to combine things using semigroups and monoids. From there, we'll talk about working inside boxes with functors, then go even further with applicatives and monads, and finally, we'll tie it all together with the big picture. Okay, so first things first, why even bother learning these concepts? What's the payoff? Well, it's all about unlocking code that is more composable, polymorphic, and predictable. Or to put it simply, code that's just easier to build, easier to reuse, and way easier to understand. You know, learning these abstractions is kind of like getting a set of universal blueprints for programming. You start to see the same fundamental patterns showing up everywhere. This lets you write one piece of code that just works on tons of different data types. That's polymorphism in action. And because these patterns follow really simple, predictable rules, you can build huge, robust applications by snapping together small, simple functions. And I love this quote because it hits the nail on the head. These aren't just some weird, abstract rules somebody made up. They are patterns that were discovered just by watching the code we write every single day. They are, in a way, the natural grammar of how good programs are built. Okay, let's get our hands dirty with our first and simplest abstraction, and it's all about one really fundamental idea: combining things. This brings us to our first fancy word, semigroup. All this really means is that you have a type of something and a consistent way to combine two of them into one. The one and only rule is that this combination has to be associative. And trust me, you already know this inside and out. When you're adding numbers, it doesn't matter if you do 1 plus 2 first or 2 plus 3 first, the result is always the same. That's associativity. It's the same deal when you're smashing strings together or merging lists. All of these are just semigroups in action. And when you look at the code for it, it's almost ridiculously simple. A semigroup is just a trait with a single method, combine. It takes two things of some type A and gives you one thing of type A back. That's it. That's the whole concept. Okay, so what if we take our semigroup and we add just one more tiny idea? Well, then we get a monoid. A monoid is just a semigroup that also has a special identity element. Think of it as a neutral starting point, a value that doesn't change anything. And again, you use this constantly. For addition, the identity element is 0, right? Because adding 0 doesn't change a thing. For strings, it's the empty string. For lists, it's the empty list. This empty or do-nothing value is the one thing that makes something a monoid. Looking at the code, you can see this beautiful relationship. The monoid trait just extends semigroup, so it inherits the combine method for free, and it just adds one new thing, this empty value. It's a perfect example of how we build up complexity from really simple, reusable ideas. So here's the crucial part. Why does this matter? Because of this. This is the magic. We can write a single generic function, let's call it fold left with monoid. When you pass it a list of integers, it automatically finds the monoid for integers and knows to use 0 as the starting point to sum them all up. But if you pass the exact same function a list of strings, it finds the monoid for strings and uses the empty string to concatenate them. One function, multiple behaviors, 0 extra code. That's powerful stuff. All right, let's climb up to the next level of abstraction. We're now going to talk about working with values that are wrapped up inside some kind of context, or as I like to call it, a box. And this is where the functor comes in. A functor is any box-like type, think option, list, or future, that lets you apply a function to the value inside it using the map method. You don't have to worry about whether the box is empty or full. The functor takes care of all of that messy logic for you. And the trait for functor just defines this map operation. It says, give me a box containing a value of type A and a function that can turn an A into a B. What does it give you back? A new box with a B inside. It basically lifts your normal functions so it knows how to work on values that are wrapped up. Okay, so functors are great for applying one function to one value inside one box. But what happens when things get more complicated? This is what takes us beyond functors and into the world of applicatives and monads. So here's the question that pushes us forward. What if you have values in multiple different boxes and you need to combine them somehow? Or what if the next thing you need to do depends entirely on the result you got from the previous step? Well, map by itself just can't handle that. And this right here is the key difference. An applicative is what you use when you need to combine results from multiple boxes that are totally independent of each other. Think about validating a username and validating a password separately, then bringing the results together. A monad, on the other hand, is all about sequencing. It's for when the steps are dependent. Think of fetching a user from a database, then using that user's ID to fetch their posts. The second action completely depends on the first. Monads are what let us chain those dependent operations together so elegantly. So, we've covered a lot of ground. Let's zoom out for a second and look at the big picture, and put everything we've just learned into a simple, coherent summary. Think of it like a staircase of abstraction, where each step builds directly on the one before it. We started with the simplest possible thing, semigroup, just combining two things. We added an empty value to get a monad. Then we learned how to map over values inside a context with functor. Applicative let us combine multiple independent contexts. And finally, monad gave us the power to chain dependent computations together. And here it is, your final cheat sheet that puts it all together. Each abstraction solves a very specific problem. Semigroup is for combining. Monoid adds a neutral element. Functor is for mapping inside a context. Applicative handles multiple independent contexts. And monads sequences dependent steps using its powerhouse operation flatmap. These 5 ideas, they're really the bedrock of modern functional programming in Scala. So I'll leave you with a question. Now that you can see these fundamental patterns of combining mapping and sequencing, where are they already hiding in your own code? And how can you start using them consciously to write even cleaner, more powerful software?